Welcome to the chapter on AC fundamentals. Alternating current, or AC, is a type of electric current where the flow of electric charge periodically reverses direction. Unlike direct current, which flows in a single direction, AC changes direction multiple times per second. AC is generated by rotating a coil within a magnetic field, which produces a current that alternates its direction. This alternating nature results in a voltage that varies sinusoidally, smoothly oscillating between positive and negative values. AC is crucial because it is the most efficient way to transmit electricity over long distances and is widely used in homes, businesses, and industries. Most of the devices we use daily are designed to operate on AC power. Understanding AC is essential for electrical engineering, as it forms the foundation for more advanced topics in power systems and electronics. In this chapter, we will cover sinusoidal waveforms, phasors, impedance, AC circuit analysis, including RLC circuits, and power and energy in AC circuits. A sinusoidal waveform is the most common type of AC signal. It can be described by the equation V of t equals V sub m sine of omega t plus phi. Here, V of t is the instantaneous voltage at time t, V sub m is the maximum amplitude of the waveform, omega is the angular frequency in radians per second, and phi is the phase angle in radians. Let's consider a sinusoidal voltage with a peak value of 120 volts, a frequency of 60 Hz, and a phase angle of 30 degrees. To calculate the angular frequency, we use the formula omega equals 2 pi times the frequency. Substituting the value, we get omega equals 2 times pi times 60, which gives us 120 pi radians per second. The phase angle of 30 degrees needs to be converted to radians, because the sine function in the equation operates in radians. To convert degrees to radians, we use the fact that 180 degrees equals pi radians. Therefore, 30 degrees is equivalent to 30 times pi divided by 180, which simplifies to pi over 6. So the voltage equation becomes V of t equals 120 sine of 120 pi t plus pi over 6, where pi over 6 represents the phase angle of 30 degrees in radians. Phasors are a way to represent sinusoidal waveforms using complex numbers. A phasor converts a time domain sinusoidal function into a frequency domain representation. A sinusoidal function V of t equals V sub m sine of omega t plus phi can be represented as a phasor V, which equals V sub m angle phi. For the previous example with V sub m equals 120 and phi equals 30 degrees, the phasor representation is V equals 120 angle 30 degrees. Impedance, denoted as Z, is the total opposition that a circuit presents to the flow of AC. It is a complex quantity that combines resistance, R, and reactance, X. The equation for impedance is Z equals R plus JX, where J is the imaginary unit. For a circuit with a resistor of 10 ohms and an inductor with a reactance of 20 ohms, the impedance is Z equals 10 plus J20 ohms. RLC circuits consist of resistors, inductors, and capacitors. The analysis involves solving for voltages and currents using impedance and phasors. For a series RLC circuit, the total impedance Z is given by the equation Z equals R plus J times omega L minus 1 over omega C. In this equation, Z represents the overall opposition to current in the circuit. R is the resistance which opposes current flow equally at all frequencies. The imaginary unit J indicates a phase shift in the reactance components. Omega, or angular frequency, shows how fast the AC signal oscillates. L is the inductance, which opposes changes in current, and omega L represents the inductive reactance, which increases with frequency. The term 1 over omega C represents the capacitive reactance, which decreases with increasing frequency. Together, these components define how the circuit responds to alternating current. Consider a series RLC circuit with R equals 10 ohms, L equals 0.1 Henry, and C equals 100 microfarads at a frequency of 50 Hz. The angular frequency omega is 2 pi times the frequency, which equals 100 pi radians per second. The impedance Z is given by 10 plus J times 10 pi minus 1 over 0.1 pi ohms, which simplifies to 10 plus J times 10 pi minus 100 ohms. In AC circuits, the instantaneous power P of t is the product of the instantaneous voltage V of t and current I of t. The average power P over one cycle is given by the integral of V of t times I of t divided by the period t. For sinusoidal waveforms, the average power can be calculated as P equals VRMS times IRMS times cosine of phi, where VRMS and IRMS are the root mean square values of voltage and current, and phi is the phase difference between them. For a circuit with VRMS equals 120 volts, IRMS equals 10 amps, and phi equals 30 degrees, the average power P is calculated as 120 times 10 times cosine of 30 degrees. This equals 1200 times the square root of 3 divided by 2, which simplifies to 600 times the square root of 3, approximately 1039.2 watts. Reactive power, denoted as Q, is an important concept in AC circuits. The formula for reactive power is Q equals VRMS times IRMS times sine of phi. Let's break it down. Q is the reactive power, measured in volt-amperes reactive, or VAR. VRMS is the root mean square voltage. This is the effective voltage of the AC signal, meaning it represents the equivalent DC voltage that would produce the same amount of power in a resistive load. IRMS is the root mean square current, which is the effective current value of the AC signal. Like VRMS, it gives a measure of the current that would produce the same power as an equivalent DC current. The sine of phi, where phi is the phase angle, indicates the phase difference between the voltage and current in the circuit. Understanding reactive power is essential for analyzing and designing AC circuits, especially those involving transformers, motors, and other components that store energy in electric or magnetic fields. In AC circuits, two key concepts to understand are apparent power and power factor. Apparent power, denoted by S, is calculated as the product of the root mean square voltage and the root mean square current, using the formula S equals VRMS times IRMS. Apparent power is measured in volt-amperes, or VA, and represents the total power that flows through the circuit, including both the power that does real work and the reactive power that does not. The power factor, abbreviated as PF, is given by the formula PF equals cosine of phi. The power factor is a measure of how effectively the power is being used in the circuit. It is the ratio of the real power, which actually performs work, to the apparent power. The cosine of the phase angle, phi, tells us how much of the apparent power is being converted into real power. A power factor of 1, or 100%, means that all the apparent power is being used as real power, which occurs when the voltage and current are perfectly in phase. A lower power factor indicates that a larger portion of the power is reactive, which means it's not doing useful work but is necessary for maintaining the electric and magnetic fields in components like inductors and capacitors. Understanding both apparent power and power factor is crucial in AC circuit design, as they help determine the efficiency and performance of electrical systems, particularly in managing energy use and minimizing losses. This concludes our chapter on AC fundamentals. Understanding these concepts is essential for analyzing and designing electrical systems. Thank you for watching.